Hello, AP Statistics students, and welcome to the College Board virtual instruction for AP Statistics. My name is Luke Wilcox. I am an AP Statistics teacher at East Kentwood High School in Kentwood, Michigan, and it is Thursday, April 23rd. I'd like to start today by saying a big thank you to those teachers and students who wished me a happy birthday. Yesterday was my 41st birthday, and we celebrated in style with a Star Wars themed birthday. My children made me this excellent Luke Skywalker cake, and then we watched Return of the Jedi, and I'm feeling very grateful at age 41 to be where I am today and to be with you all today. So thank you for that. We do have a lot lined up for today. We're talking about sampling distributions. So I'd like to go ahead and just jump right into the lesson for today. So checking to make sure we're in the right place. This is AP Statistics. You all know who I am at this point, I hope. A few quick reminders for those that may be here for the first time. This is a daily meeting that we have at 2 o'clock Eastern Standard Time. We are reviewing for the AP exam, and we are in this week right here, April 20th through the 24th, where we're covering units 4 and 5 from the College Board CED, which will complete our review of all of the content contained within the CED, which means that next week, Mr. Murphy and I have some special things planned for you, some general review things that I think are going to be super helpful. And then that final week, we're actually going to give you some practice questions that might look very similar to the questions that you're going to see on your modified AP exam this year. And of course, the big day, the big game, May 22nd, is when you all will be taking your AP Statistics exam for 2020. So a quick note here that all of the lessons that you see on YouTube Live are available to download at statsmedic.com/YouTube. There, you just have to know the date and you will be able to find the resources to be able to print those out. And then a final reminder here that if you or another student that you know is in need of a device or internet access in order to be able to take that AP exam at home on May 22nd, the College Board wants to make sure that you have that. So if you just go to cb.org/tech, there's a form that you can fill out and they will make sure that you are taken care of. All right, so let's take a look at the homework from the previous lesson. This is the assignment that you got from Mr. Murphy yesterday. And it's a good lead in into some of the stuff that we're going to talk about today. So here's what it says. A company sells concrete in batches of 5 cubic yards. The probability distribution of X, the number of cubic yards sold in a single order for concrete for this company, is shown in the table below. So we see there are only a certain number of values possible for X, which would be 10, 15, 20, 25, and 30. And then we see those respective probabilities for each one of those values for the random variable X. Okay, the rest of the question says, expected value of the probability distribution of X is 19.25. Okay, so what they're giving us there when they say expected value is they're giving us the mean of that value. And then they're also giving us the standard deviation of X. There is a fixed cost to deliver the concrete. The profit Y in dollars for a particular order can be described by Y equals 75X minus 100. What is the standard deviation of Y? Okay, very important here. The relationship that they've given us for Y is that Y is equal to 75X minus 100. Now let's think about how the distribution of Y is going to compare to the distribution of X. Well, really there's two things that we're doing to that X value in order to turn it into a Y value. The first step is to take that X value and multiply by 75. So we could take each one of these X values and multiply by 75. And what we want to know is what is that going to do to the standard deviation? Well, if you take a list of numbers and you multiply them all by 75, sure enough, that's going to multiply the standard deviation by 75. So we know in order to get the standard deviation of Y, we're going to have to take 75 times the standard deviation of X. But now we need to consider the next step here, which is to subtract 100. Well, here's the deal. If you subtract 100 from all of the values in a list, all you're really doing there is shifting the distribution 100 units down. That's not going to change the variability. So really, this part here does not have an impact on the standard deviation of Y. And sure enough, this is all we need in order to find the standard deviation of Y. So I'm just going to take 75 times the standard deviation of x, which we know from the problem is 5.76, and we are going to get a standard deviation of y equal to $432. So looking at my answer choices over here, I can see that B is the answer that I'm looking for. Now, the most common incorrect answer, I will tell you for sure, because I've seen students make this mistake, is they will subtract 100 because they think that this minus 100 also subtracts 100 from the standard deviation, which is not true. So this is definitely the incorrect response there. The correct answer is B. So hopefully you did okay with that. And I think we are now ready to talk about some new learning for today. So here is the quick lesson overview where I will start with the learning targets. And there are 3 of them today. The first 2 are very parallel. So let's take a look. Learning target number 1, describe the sampling distribution of p hat and then p1 hat minus p2 hat. So this first learning target is all about proportions, and it's about sampling distributions for proportions. Now look at the second learning target. Once again, sampling distribution, but this time x bar and x1 bar minus x2 bar. So this learning target is all about sampling distributions for means. And then sort of a sub-learning target underneath that is to understand the central limit theorem, which is going to relate back to the sampling distribution for means. So let's go ahead and jump right in on this one. Okay, page 1 of the activity here today. The question that we're trying to answer is, do you like Reese's Pieces? And I will be honest with you, my 11-year-old daughter, Reese, yes, her name is Reese, guess what? Her favorite candy is Reese's Pieces. And one day she claimed to me that she really likes the orange ones better than the other 2. Now, I'm not convinced that that's true, but I started to wonder about the distribution of the color of Reese's Pieces. And I looked it up, and it turns out that the candy manufacturer claims that 40% of the candies are orange. So they're not equally distributed, okay? So first of all, you can see we are in the world of proportions here. 40% is our proportion that's being claimed for the whole population of all Reese's Pieces. And so let's be careful with our notation here. The notation we should be using here is P for the true proportion for the whole population, right? As opposed to P hat, which would be the sample proportion. So we're going to use an applet to simulate taking random samples of 50 Reese's Pieces. Well, this very clearly is our sample size, and we're going to use lowercase n to represent that sample size of 50. So here's the definition of the random variable. It says let n equal the number of orange candies in a sample. Number of orange candies. So we're looking for how many out of those 50 are orange. So question 1 says use the applet to take 100 samples of 50, sketch the results below. So I'm going to take you now to the applet, and you can just follow along on your screen here. And you can find this on the internet if you just type Reese's Pieces applet. This will be the first one that comes up. And I've already set our probability of orange to 0.4 and our number of candies to 50. And let's just go ahead and take one sample and see what it looks like. And what I really like about this applet is that there is an animation so you can physically see the random sample of 50 Reese's Pieces. And we're splitting them into 2 buckets, the orange ones and then the not orange ones. And then you can see here that the applet will count up the number of orange candies, in this case, 16 out of the 50. And then down here on the bottom, you can see it's putting a tiny little dot right at 16. So let me show you one more of these. We're going to take another random sample of 50 Reese's Pieces, count up the number of orange Reese's Pieces. And for this particular sample, we got 19. And down here, you can see that there is a dot that appears at 19. Now, the nice thing about technology is that we can do many, many samples very, very quickly. And we want 100 total, and we've already done 2. So I'm going to add 98 more samples here, making sure to unclick the animation. Otherwise, we'd be watching this for the rest of the hour here. I'm going to draw those samples real quick. And here is the distribution. And so let's notice a couple of things here. First of all, it appears that the center of this distribution is looks like it's about 20. and as low as maybe 10 is the lowest value, 29 is the highest value. And I'm starting to see a little bit of a normal distribution here. In fact, I can click this and it shows me that there is a little bit of a normal distribution that's appearing there. So let's go ahead back to the activity and let's copy this down. And here's the thing. We don't have to copy it exactly what we saw. We just need the general idea of what that looked like. So here's what I remember. I remember that the tallest stack of dots was at about 20. So I'm just going to draw some dots at 20. I knew the lowest one was maybe about 10 and the highest one was maybe about 29. And then it appeared to have somewhat normal distribution. Certainly not perfect, but I'm just going to sketch this in. And this just has to be a sketch. Certainly does not have to be exact to what you see in the applet. This is just giving us an idea of what this distribution looks like. So the first question to answer here is name the distribution. Well, I'm hoping that this looks very familiar to the lesson that we went over on Tuesday, where we talked about binomial distributions. Sure enough, this is in fact a binomial distribution. And just as a quick review, to make sure that this is a binomial distribution, there are 4 conditions that need to be checked. And we remember that with the acronym BINS. B stands for binary. So each trial is a success or failure. In this case, a success is orange and a failure is not orange. I stands for independent. Well, we have a random sample, so each trial should be independent. And because we're sampling without replacement, the 10% condition should be checked. And certainly 50 is less than 10% of all Reese's Pieces. So I'm going to say the independent condition is met. N, the number of trials, is fixed. Well, here the number of trials is 50 because we're sampling 50 Reese's Pieces. And then S, we have the same probability of success for each trial. And the probability of success here we know is 0.40. And so that condition is satisfied. So we have a binomial distribution. So we're going to be able to use some things from Tuesday to help us answer the rest of the questions for this distribution. Now, what does each dot represent? Well, let me take like this dot right here, for example. What does that dot represent? Well, it represents a random sample of 50 Reese's Pieces, and then we count the number that are orange. In this case, there were 12. And then this dot represents a different random sample of 50 and counting up the number of orange. And this is a different random sample, and this is a different random sample, and this is a different random sample. So to answer the question here, what does each dot represent? It represents one sample of 50 Reese's Pieces. And then what we're going to do with that sample is we're going to count the number of orange. And we are calling this random variable n. And so what we have in this distribution is many, many samples, right? So there is another name that we could give this distribution, and that is what's called a sampling distribution. And in this case, each dot represents a different n value. I'm going to call this the sampling distribution of n. Now, a little bit of a disclaimer here. In order for this to be the true sampling distribution of n, we must have all possible samples of size 50. Well, obviously, there's like an infinite number of samples of size 50, so we don't have the true sampling distribution here. But you know, I think that these dots give us a good enough idea about the sampling distribution that I'm comfortable calling it a sampling distribution, even though it's not the true sampling distribution of n. Now, I'd like to be able to describe that sampling distribution. And let's start with the shape. And we've already mentioned here that we think that the shape of this thing is approximately normal. And actually, if I remember back to the lesson from Tuesday when we talked about binomial distributions, there's actually something that we can check to make sure that the normal approximation is appropriate here. That's what's called the large counts condition. And remember, the large counts condition says that n times p, 50 times 0.40, which is 20, and then n times 1 minus p, which is 30, has to be greater than or equal to 10. And that's really telling us the expected number of successes and the expected number of failures are both greater than or equal to 10. And sure enough, they are here. And so I'm comfortable saying that this distribution is approximately normal. So that takes care of the shape. Now let's talk about the center of the distribution by thinking about what the mean is. And just by looking at the picture here, I can see that the mean is 20, right? You can very clearly see that. But if you recall from Tuesday, we did have a formula for calculating the mean of a binomial distribution, which is n times p. And actually, we know n times p over here is equal to 20. So that confirms our answer and what we see in the dot plot there, that 20 is the mean of this distribution. Now let's go ahead and move to the standard deviation of the distribution. And once again, I'm going to go back to our previous lesson on Tuesday. There is a formula for calculating the standard deviation for a binomial distribution, which is square root of n times p times 1 minus p. So all we have to do here is plug in some numbers. Square root of n is 50, p is 0.40, and 1 minus p is 0.60. And if you plug that into your calculator, you're going to get a standard deviation of 3.6. Now, one little warning here is that when you're plugging in a number for n, you want to be careful that you're using the sample size there. And often students will have trouble deciding whether it should be 100 or 50. We want the sample size, not the number of samples. So 50 is the appropriate value for n, which is what we used in our calculations. So we are ready to move on to number 2, which says, let p hat equal the proportion of orange candies. Notice what's changed here. We are no longer looking for the number of orange candies. We are looking for the proportion of orange candies in the sample. So the question is, what needs to be done to each value of n to change it into p hat? Well, if I look at my values for n, which represent the number of orange candies, and I want to change that into a proportion, all I need to do is divide by the sample size, 50. So the answer here is that we just need to divide each n value by 50, and that'll change it into a proportion. So number 3 says, in the applet, change from the number of orange to the proportion of orange. So I'm going to take us back to that same applet that we were using, and we've still got our dot plot here. And what I'm going to do is I'm going to change from the number of orange candies into the proportion of orange candies. And what I want you to do is I want you to watch this dot plot here. Okay, watch what changes. So here we go. I'm going to go ahead and change to proportion. And what did you notice? Let me do it again. There's the number of orange candies. There's the proportion of orange candies. Hopefully what you noticed is that the dots did not change at all. They were exactly the same as they were before. But what changed was the values on the x-axis. Instead of being the number of orange candies, we now have the proportion of orange candies. So let's go ahead and copy that into the activity here. And once again, this is just a sketch. And hopefully you noticed in our simulation there that 0.40 was right about the center of the distribution. So I know I have my tallest number of dots there, and I had dots as low as this and maybe as high as this. And really what I'm trying is to copy the dot plot from above, but just put it on the new scale here where we have proportions instead of the number of orange candies. All right, so there we go. So before we name the distribution, I actually want to think about this question first. Okay, what does each dot represent? So let's take, say, this dot, for example. Well, that is a random sample of 50 Reese's Pieces and the proportion of orange calculated from that sample. And this is a different random sample of 50 and the proportion calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. So we're going to say here each dot represents one sample. And then what we're going to do with that sample is we're going to calculate the proportion of orange. And being careful with our notation here, because it's a sample proportion, that would be p hat. So Over here, each dot represents a different sample and the proportion calculated from that sample. So we can call this distribution the sampling distribution of p hat. Remembering that it's not the true sampling distribution because we don't have all possible samples of size 50. So that is the name of the distribution. This is what's called the sampling distribution of p hat. Now let's see if we can go ahead and describe that distribution. And I'm going to start once again with the shape. And of course, the shape is exactly the same as the shape of the one above it because it's the same distribution, just a different scale. So of course, I can say that this is approximately normal. And my justification would be the large counts condition. We already checked that above. So the large counts condition also allows us to say that the sampling distribution of p hat is approximately normal. All right, now let's move to the mean of the distribution. Okay, the mean of the distribution. Well, let's think about this. What did we do to all of the values here in order to turn them into these values here? We divided each one of them by 50. So what do you suppose that's going to do to the mean? Probably going to divide it by 50. So what I'm going to do is I'm going to take the mean from above, which was 20, and I'm just going to divide it by 50. And that's going to give me 0.40, which sure enough is exactly the value we see at the center of the sampling distribution. And so this is actually giving us an important formula here. It's the formula for the mean of the sampling distribution of p hat. And what we did was we started with the formula for the mean of a binomial distribution, which is n times p, and then we divided it by 50. Well, in this case, if we're generalizing, we're dividing by the sample size. The n's cancel out, and what we end up with is that the mean of the sampling distribution of p hat is just equal to p, the true proportion. Okay, let's go ahead and move to the standard deviation. And we want to know the standard deviation of the distribution. Well, once again, what did we do to all of these values to turn them into these values? We divided them by 50. What do you think is going to happen to the standard deviation? It's going to be divided by 50. So I'm going to take my standard deviation from above, 3.46, and I'm just going to divide it by 50. And that's going to give me an answer of 0.07 for my standard deviation. Now let's see if we can generalize that into a formula here. Okay, the formula for the standard deviation of p hat. Well, we started with the formula for the standard deviation of a binomial distribution, which is the square root of n times p times 1 minus p. And then we divided it by 50. Well, to generalize, we're going to divide it by n. And instead of dividing by n, I'm just going to put a 1 over n out in front of it, which is the same as dividing by n. Now here we're going to have to use a little trick from our algebra class, which is to take this 1 over n and put it inside the square root. Now when it goes inside the square root, it becomes 1 squared over n squared, or just 1 over n squared. And then we still have n times p times 1 minus p. Well, we can do a little simplifying here. One of these n's down here is going to cancel with this n. And look, we are left with a formula now for the standard deviation of p hat. It is the square root of p, 1 minus p on the top, and then n on the bottom. So this is the formula for the standard deviation of the sampling distribution of p hat. Okay, we've got one final question here, and here's what it says. Suppose that we took an SRS of 50 Reese's Pieces and calculated the proportion that are orange, and an independent SRS of 100 Skittles and calculated the proportion that are orange. Describe the sampling distribution of p1 hat minus p2 hat. So look, now we have two samples. So this 50 is the sample size of the Reese's Pieces. I'm going to call that N1 because that's our first sample. 100 is the second sample. I'm going to call that N2. And then we've got sample proportions for each one of those. And we want to be able to describe the sampling distribution of the difference between these two sample proportions. Well, let's go ahead and handle this like we do anytime we describe a distribution. Let's start with the shape. And sure enough, it turns out that this shape Well, you can check to see if it's going to be approximately normal in the same way that we did up above, but we have to do it for both sampling distributions. So that means that N1 P1 and N1 1 minus P1 for the sample of Reese's Pieces has to be greater than or equal to 10. But we also have to check it for the second sample, N2 P2 and N2 1 minus P2 have to be greater than or equal to 10. If all four of those are true, we can say this sampling distribution is approximately normal. Okay, next we're going to move to the center of this sampling distribution. And then in the end here, we will also get to the variability. Now, in order to get some formulas for the center and the variability, I have to take you back to something that Mr. Murphy talked about yesterday when you were talking about combining random variables. And here's what we're going to do. We're going to think of this as being random variables here. And what we're doing is we're taking the difference between two random variables, x minus y. And if you recall from yesterday's lesson, if you want to get the mean of the difference between two random variables, very straightforward. You just take the mean of x minus the mean of y. So that means for us, if we want to get the mean of P1 hat minus P2 hat, we just need to take the mean of each one of those distributions and subtract. And we know from above this formula here that the mean is just the true proportion. So we have the true proportion for the first population minus the true proportion for the second population. And there is our formula for the mean of the sampling distribution of P1 hat minus P2 hat. Now for variability, once again, you got to go back to yesterday's lesson with Mr. Murphy. And hopefully you remember that when you have the difference between two random variables, it actually increases the variability. There's more variability. And so the question is whether you want to add the standard deviations or add the variances. And very important here, one does not simply add standard deviations. What we do add is we add the variances. So we know here that we want to go ahead and add the two variances. So the formula is to get the variance of x minus y. We do the variance of x plus the variance of y. Now what that looks like here, if I'm trying to find the standard deviation of P1 hat minus P2 hat, I need to add variances. Well, right here, I have the formula for standard deviation. In order to turn that into a variance, I'd have to square it. Well, squaring it is just going to get rid of the square root. So the square root goes away, and what we end up with is P1, 1 minus P1, all over N1. That's the first variance, plus the variance of the second population, P2, 1 minus P2, all over N2. Now that's giving me the variance. In order to now turn that back into the standard deviation, I need to take the square root of that big long formula there. And so now we have our formula for standard deviation. So a lot of formulas that you see here, but no fear, these formulas are in fact provided for you on the formula sheet for the AP exam. So if you go to the second page of the formula sheet, the very top here, you are going to see all of the formulas that you need for the sampling distribution for proportions, which is what we just talked about. So if you have one sample or one population, there's your mean and there's your standard deviation. And then if you have two samples, there's your mean and there's your standard deviation. And those match with the formulas that we came up with in the activity. So that completes page number 1, dealing with proportions. You probably know what's coming ahead here on page number 2. We are now going to enter the world of means. So there's a little bit of a setup, and we're going to use a different applet for this one. So here's what it says. Follow along with me. Reese's Pieces are available in snack size bags. Assume that the number of total candies in each bag follows a normal distribution with a mean of 16 and a standard deviation of 5. Okay, let me pause right there. The mean of 16, now they're talking about the mean of the population of all bags of these snack size. So we're going to use the right notation here, which is mu, and we know that's equal to 16. And then this is the standard deviation of the population. So we're going to use sigma, and we know that's equal to 5. So we will use this applet to simulate taking random samples of snack size bags. All right, so here we go. Let X equal the total number of candies in a randomly selected snack size bag. Sketch the distribution below. Okay, you're going to have to see what this looks like in the applet here. So let me jump over to the applet. And this is the applet that we're going to be using here. And that first distribution that you're seeing right on the top there, that's the distribution of all of the bags of snack size Reese's Pieces, counting up the number of total candies in each bag. And sure enough here, you'll see that on average, there's going to be 16 candies in each bag with a standard deviation of 5. So they're calling this the parent population. We're going to call it the population distribution. And so the first thing we need to do in the activity is we sketch this distribution here. And once again, this is going to just be a sketch, does not have to be perfect, but we clearly know that it looks like a normal distribution. So we know 16 is the mean. So I'm going to draw the biggest bar at 16. And then the bars get lower and lower as we move to the right. And they get lower and lower as we move to the left. So it looks something like this. And don't worry about that being perfect. Just get the general idea down there. And first we want to name the distribution. And I told you already, we are going to call this the population distribution because it represents the population of all snack size bags of Reese's Pieces. Now, what does each black box represent? Well, you can't really see it in the applet, but there's really a bunch of black boxes stacked on top of each other here. And the idea is that, say, this black box right here represents one bag, one snack size bag of Reese's Pieces with maybe 14 total candies in it. And this one has 20 candies in it. And this one has 25 candies in it. So we're going to say that each black box represents one snack size bag. And what we're going to do is we're going to count the total number of candies. And we're calling that random variable X. Okay, let's talk about, or see if we can describe this distribution now. The first thing that we want to talk about is the shape of the distribution. And we actually already know that the shape of this distribution is approximately normal. And the reason I know that, if you look above, they actually tell you this right in the problem. So I'm going to say that this is given in the question. Okay, we are given that the population distribution is approximately normal. Now, what is the mean? Well, we can see here by the picture that the mean is 16, but we also knew that the mean is 16 because that was given in the problem. So let's identify the mean here as being 16. And what's the standard deviation? Well, that's also given to us in the problem. We know the standard deviation of the population is 5. Okay, so now let's move down to the next part where it says let X bar equal the mean number of candies from a random sample of 5 snack size bags. So we are going to take a sample of 5 snack size bags, count the number of candies in each one, and find the average from those 5 bags. So it says use the applet to take 10,000 samples of size 5. Well, let me jump back to the applet here. And let's see if we can take a bunch of samples here. So we want to start out with a normal distribution here. And I'm going to go ahead and click animated here and notice what happens. We've got a sample of 1, 2, 3, 4, 5 bags of Reese's Pieces. And then this blue box represents the average number of candies for those 5 bags. Let me show you another one. Here is a different random sample of 5 and the mean calculated from that sample. And this is a different random sample of 5 and the mean calculated from that sample. And what I can do is I can do this over and over and over again, 10,000 times, each time taking a sample of 5 and then dropping down the mean from that sample of 5. And so this is the new distribution that we want to look at. And the first thing that you'll notice is it does look like it's approximately normal, just like the population distribution. But very clearly, it has a lower variability there. So let's take some of those ideas back to the activity now. And the first thing we want to do is to just sketch a picture. Now, it still appeared to have a mean around 16. And so my tallest bar is going to be there. But it had a lower variability. So I'm going to make this distribution much skinnier than the one above it. Right? Definitely had a lower variability than the population distribution. So let's go ahead and answer some questions about this. The first one, I'm going to actually start here. What does each blue box represent? Well, let's say we look at this one blue box right here. That box represents a random sample of 5 bags and the mean number of candies calculated from that sample. And this is a different random sample of 5 and the mean calculated from that sample. And this is a different sample, and this is a different sample, and this is a different sample. So what does each dot or blue box represent? Represents one sample. And then from that sample, we're going to calculate the mean number of candies. And the correct notation here for the mean number of candies from the sample is X bar. So what we have over here are many samples of size 5 and a mean calculated from each one of those samples. And so sure enough, we can call this a sampling distribution. Okay, once again, it's not the true sampling distribution, but I'm comfortable labeling it as such. So to name the distribution, we're going to call this the sampling distribution of X bar. Now let's see if we can describe that distribution. And I'm going to start with the shape. And we noticed right away the shape was also approximately normal. And if I had to justify that, I would say because the population distribution is approximately normal, which we were told in the problem. Now, what is the mean of the distribution? Well, you can tell just by looking at it that the mean is 16, just like the mean of the population distribution. And so we actually have an important formula here, which is the formula for the mean of the sampling distribution of X bar, which is just equal to the mean of the population, mu. Now, when we move down to standard deviation here, we know the standard deviation of the population distribution is 5. And very clearly, the variability has decreased, right? So we want a number less than 5. So it might make sense to divide by something. And it seems reasonable that the sample size has something to do with it. The bigger the sample size, the lower the variability. So you might think that we would want to divide that by the sample size. Well, it turns out that it's actually divided by the square root of the sample size. And that has to do with that whole business about adding variances. But that's going to give us the correct value for the standard deviation here, which is 2.24. And so the formula, if we generalize this, for the standard deviation of X bar is to just take the standard deviation of the population and divide it by the square root of n. All right, now let's move on to number 7. It says change the parent population to be skewed instead of a normal distribution. All right, so I'm going to go back to the applet now, and I'm going to change the parent population. Instead of being a normal distribution, let's say that it were skewed, and you can see here skewed to the right. Now, first, let's just acknowledge that this would be unfortunate because now the average number of candies you're getting in a bag of Reese's Pieces is only 8. Okay, a little bit unfortunate. So let's see what happens when we take samples of size 5. So once again, sample of 5, find the mean, drop it down, right? I'm going to do that 10,000 times real quick. And what do you notice? Well, definitely less variability, but I still think I see a little bit of a skew to the right on this one, okay? Now let's see what happens when we increase the sample size. So down here, I'm going to change my sample size to 25, and it's going to do 2 different distributions for me. The first one is samples of size 5. The second one is samples of size 25. And what do you notice down here? Well, once again, less variable because our sample size went up, but also it's starting to look like it's approximately normal. So the amazing thing here is that even though the parent population is skewed to the right, the sampling distribution is approximately normal, if your sample size is big enough. So let's go ahead and capture those thoughts in the activity here. All right, number 7, samples of size 5, describe the shape of the sampling distribution. Well, for the first one, the samples of size 5, it was still a little bit skewed right. So I'm going to say slightly skewed right. But the amazing thing was when we jumped down to samples of size 25, the sampling distribution appeared to be approximately normal. So number 9 says, what happens to the shape of the sampling distribution as the sample size increases? Well, here's the deal. As the sample size goes up, the shape of the sampling distribution becomes closer to a normal distribution. And this very, very impressive fact is one of the biggest ideas in introductory statistics and is what is called the central limit theorem. The central limit theorem says, as your sample size increases, the sampling distribution gets closer and closer to normal, no matter what the population distribution looks like. Skewed left, skewed right, bimodal, doesn't matter. Now, how big of a sample size do we need in order to be comfortable saying the sampling distribution is approximately normal? Kind of depends on who you ask or what book you look in. One of the generally accepted values is that if n is greater than or equal to 30, you're usually pretty safe there. All right, last question here, number 10. Suppose that we took an SRS of 25 Reese's Pieces snack size bags and calculated the mean number of candies, X1 bar, and an independent SRS of 40 Skittles snack size bags and calculated the mean number of candies. Okay, you can see the parallel to what we talked about on the previous page. We now have 2 samples. So let's go ahead and talk about the shape, the center, and the spread for this distribution. And I'm going to write it as variability here. Okay, first of all, for the shape, we're going to hope that somehow we can arrive at the fact that it is approximately normal. And there are a couple of different ways to arrive at that, which I will summarize when we get to the important ideas. Now, for the center of the sampling distribution here, we want the mean of X1 bar minus X2 bar. And really, we just need to take the mean of the first distribution minus the mean of the second distribution. And we know up here that the mean is just mu. So it's just going to be the mean of the first population minus the mean of the second population. Now, for the standard deviation of X1 bar minus X2 bar, you might think that you need to subtract standard deviations, but we know that the variability increases, so we need to add. But remember, one does not simply add standard deviations, we have to add the variances. So I need to take this and turn it into a variance by squaring it. So that's going to give me sigma 1 squared over n, because this square root is going to go away. And then I need to add the variance of the second distribution. This should be 1, this should be 2. Now that gives me the variance. In order to turn it back into standard deviation, I just need to take the square root of that whole thing. Now, once again, a lot of formulas there, but the nice thing is that on your formula sheet here, the next thing you see is sampling distributions for means. If you have 1 sample, there are your formulas. If you have 2 samples, there are your formulas there. So let's see if we can go ahead and summarize our learning from today's lesson. So here's how I'm going to organize the important ideas. Of course, this is all about sampling distributions, but there are 2 different worlds in the sampling distributions. There is the world of proportions, and there is the world of means. And what I'd like to do here is to compare how those 2 sampling distributions look in terms of 3 very important things: the shape, the center, and the variability. So let's start with the shape of the sampling distribution for a proportion. And we decided that hopefully we can arrive at the fact that it is approximately normal. And the way that we check that is by using the large counts condition, just like we did for the binomial distribution, which says that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Now for the sampling distribution of the mean, once again, we would like to arrive at the fact that that sampling distribution is approximately normal. But we have a couple of different ways that we can arrive at this. The easiest way, and the way we used in the activity, is that we were given in the problem that the population distribution is normal. So of course, if the population distribution is normal, then the sampling distribution is approximately normal. The second way, which we arrived at the end of the activity, is using this idea of the central limit theorem, that if your sample size is large enough, so I'm going to say here, sample size is large, and for most textbooks, that's n greater than or equal to 30, then by the central limit theorem, CLT, we know the sampling distribution is approximately normal. Now, there is a third special case where you don't know anything about the population distribution and your sample size isn't big enough. We're less than 30. In that case, you need to make a graph of your sample data, a dot plot, a histogram, a box plot. And what you'd like to see is that the sample data show no strong skew or outliers, which would mean that it's reasonable to assume that that sample came from a population distribution, which is approximately normal, which then allows us to say the sampling distribution of X bar is approximately normal. Okay, now let's move to the center. This one will go pretty quickly. The center of the sampling distribution for p hat is just the true parameter, the true proportion of the population. Over here for means, the mean of the sampling distribution of X bar is just equal to the true mean of the population mu. And then finally, let's write our formula for standard deviation as a measure of variability. Standard deviation of p hat, which we arrived at in the activity, is the square root of p 1 minus p all over n, which we derived from the binomial distribution formula for standard deviation. And then over here for means, the mean of X bar is equal to sigma over the square root of n. Now, I've just given you the formulas for one sample. We did also derive the formulas for two sample. I'm not going to put those into the important ideas. You can always look those up in the formula sheet for the AP exam. Now, we have a homework question for you here. It is a multiple choice. If you could try that before tomorrow's lesson. I will be with you once again tomorrow. Tomorrow is going to be FRQ Friday, which means I'm going to bring 3 of my favorite FRQs. And we're going to go through how to look at a model solution, but also the rubrics that are used to grade those. So I certainly hope that you'll be with me again tomorrow, and have a good evening.